Hello, this is a video tutorial for example 3 and the series solutions to differential equations presentation, and this is my favorite out of all three. This is sort of a classic example for all sorts of methods for finding solutions to ordinary differential equations. It's not a boundary value problem, so we don't have to worry about that. We can keep it just to constants, but we're given y double prime plus y is equal to 0. So everything is really convenient. All the coefficients are 1 where we want them to be, and otherwise really easy to just write directly as a series. That's what I'm going to do first thing. So this is the second derivative. So it starts at index 2, and it's going to be cn n times n minus 1 times x to the n minus 2. Remember, power series differentiate with the power rule, but because in this case the first couple terms are 0, we don't care about non-zero terms, so we start at a higher index that's not 0, right? And then y is just y is this normal power series sub n x to the n, and that is all equal to 0. So just like both examples before and every example ever, we can use what we know about sums to add 2 here and subtract 2 here to get the starting index and the power on the variable the same, and write it as a single infinite sum. I'm going to go ahead and do that both in one step. This becomes c sub n plus 2 times n plus 2 times n plus 1 times x to the n, right? And this remains unchanged, right? On the homework, there is an example where you do have an x in one of these, and you basically just add 1 to the exponent, because if our exponents work, and you do that step accordingly, nothing changes, nothing special. Going back to this one, I'm going to write it as a single infinite series and pull out the x to the nth power. Right? So this is all still part of the same series, and this is all still equal to 0. Now the implication from this, right, zero product property all the way back from, what was that, high school algebra, middle school algebra, this implication is that c sub n plus 2 times n plus 2 times n plus 1 plus c sub n is all equal to 0. Well, just like, again, all the examples before and all that will ever be, we just solve for a recurrence relationship. This is the highest thing in the subscript. Therefore, we can say that c sub n plus 2 is equal to negative cn over n plus 2 times n plus 1. Now, you can multiply these out if you want. I just don't. I think it's easier just to leave them not multiplied to find values. But that's actually not what I'm going to do. I know in the other two examples I drew charts out, and I said n is over here and c sub n plus whatever is over here. I'm not going to do that this time, but the important thing that we need to know is we get a pattern between even terms and odd terms. And if we were to do a chart where we just go from values of n from 0 up to whatever, and we find the c sub n plus 2 term, right, we find that, what we're going to see is a pattern between even and odd terms. Now this should make sense based on what we talked about in class, but the even terms, we'll say even in scare quotes here, are going to be represented by this series. It's going to be the sum from n equal 0 to infinity of negative 1 to the n over 2n factorial x to the n times c naught, right? And very, very similarly, the odd terms, again in scare quotes, are going to be represented by the series n equals 0 to infinity of negative 1 to the n over 2n plus 1 factorial times x to the 2n plus 1. This is supposed to be a 2n up here. So let's fix that. My mistake. It's supposed to be a 2n. Right, and then times c1, where c0 and c1 are basically arbitrary constants because, again, no boundary condition specified, so we can leave them as such. But these are really special because that means y is just the sum of these infinite sums, right? So I'll just say C naught times, because it's a constant, remember I can bring it out, equals 0 to infinity of negative x, nope, sorry, negative 1 to the n, x to the 2n over 2n quantity factorial plus, let's do it down here, C1, again a constant, bring it out, and front because I want to, right, and x to the 2n plus 1 over 2n plus 1 quantity factorial. And this is the solution as a series to the ordinary differential equation y double prime plus y equals 0. But this doesn't really tell us much. And in fact, the question wants us, it specifies to express our solution as transcendental functions. Now, by the time that this video goes up and the time that this presentation happens, I don't know if we've covered this in class, so if the Taylor series and Maclaurin series don't sound familiar, this is not important. But if chance we have, this is the next part, the last part of the question. Both of these are the Maclaurin expansions of cosine and sine respectively, or the Taylor series of both of those functions respectively center at 0. So recall that we have, when thinking about Maclaurin series specifically, we can say that cosine of x is the infinite series from n equals 0 to infinity of negative 1 to the x. Sorry, that's supposed to be to the nth power. X to the 2n over 2n factorial. And that sine x is very similarly the infinite series from n equals 0 to infinity of negative 1 to the n, x to the 2n plus 1 over 2n plus 1 quantity factorial. And lo and behold, that's exactly what we have in our series solution for this. Now, we have a constant out front that's each of them are multiplied by, but that's easy because we don't have a boundary condition to work it out. So now, knowing that these are true statements, these are both true, right? These are the Maclaurin expansions for these two functions, and they are transcendental. That means we can finally go through with the end of the question. So, knowing that this is true, and knowing that everything we found up here is valid, we can then say that y is just c naught cosine of x plus c1 sine of x, where c naught and c1 are constants. And that is the solution to this ordinary differential equation, y double prime plus y equals 0, without any sort of boundary condition where these are both constants again. Now, this should make perfect sense, right? Because if we consider trig functions and how when you differentiate them, they're cyclical and how this is a differential equation, this should make sense, right? If we let y equal whatever, if we impose a boundary condition that says y is just sine, this should make sense, right? Because the second derivative of sine is just negative sine plus sine is 0. This should make perfect sense because trig functions are cyclical. So think about that, try to intuit it. This is a really, like I said, sort of a classic differential equation, and I think it's a great example to show for series solutions of differential equations.